All right, so here's a recording of today's lecture, though done after the fact. And the big problem that we tried to get through during class, and many of you did, but I feel like there's some people who are really getting it, some people who are sort of like, maybe, and then some people are like, I have no idea. And so I really wanted to take some time to go through this for y'all. So if we're looking at the circuit here that we want to simplify, remember that we want to find the things that are going to be in parallel, definitely, or in series, definitely, individual components. And because we can go from the right-hand side of L5 to L3, that means that the right-hand side of those two light bulbs must be at the same voltage. And if we go from the left-hand side, use a different color here, to the left-hand side, we can do the same thing. They must be at the same voltage because they are connected just through wire. We don't have to go through anything that would change the voltage value. Okay, so these two components are definitely in parallel with one another. And so that means that we can combine them. When we do that, let me grab a different color here. That's fine. When we do that, what we get is that the resistance of R3 and 5, so R3, 5, is R3 over R5, and that's 1 over 10 plus 1 over 10 because we're saying they're individually 10 ohms. And that means that this is 2 over 10, and then we have to invert the whole thing, right, to get R3, 5 combined, and that is 5 ohms. Great. All right. So that means that we can redraw this circuit with just 3 and 5 combined into a single resistance that is 5 ohms in size. So what that looks like is this, and I'll try to be quick about it here. So this right here is 5 ohms, and the rest of it looks exactly like it did before. Okay. Now the next step is to realize that 4 and 5 of this 5 ohms, the combination of L3 and L5, are in series, right? Once the current goes into this branch, it can't get out to go back to the negative of the battery without going through both of those things. It doesn't get used up or anything like that. Voltage is what's used up. Voltage represents a certain amount of energy per charge. It gets used up as you go around a circuit. Current does not, right? Whatever flows in, like the flow of a branch of a river or a pipe, water in a pipe, that all stays the same, okay? So R4 plus R3, 5, that's our rule, right? We just sum it up for series resistances, is 10 plus 5, and that gives us 15 ohms. And that means that we can combine these two things. Once we combine those two things, I think it's pretty easy to see that this, right, that combination can be connected to 2 just through wire. And on the other side, it can be connected to 2 just through wire, going over no other things that either produce or use electrical energy. And so we can combine those two things into another parallel combination, except this time we're putting together a whole bunch of stuff. So let's get it right here. So 1 over 2, okay, all those things, right? This here being R3, 4, 5, okay? So that's 1 over 10, that's 1 over 15, and once we add those up and invert them to get this, okay, then we find that the combination of 2 and 3 and 4 and 5 give us 6 ohms of resistance. That's an ohm. There we go. Okay. Lastly, I'll redraw the circuit one more time. What we've got is this. Where this is this resistance. Now that circuit we've been able to solve for many moons, and so the total resistance is going to be 10, the resistance of the first light bulb, 10, the resistance of the number 6 light bulb, plus this equivalent resistance for a total of 26 ohms. Okay, hopefully that helps out, and please let me know if the technique here, any portion of it, identifying what's in series and parallel, where the currents are going, whether voltage is the same on across, or voltage difference is the same across two items, all of that kind of stuff. Those are important skills for analyzing these circuits, and are going to allow you, if you're reasonable at them, to solve all kinds of problems on assignments and quizzes and exams and things like that. So yeah, drop by office hours or whatever if you're still noodling about some portion of this question. But the other part of the lecture today was about batteries. And batteries we haven't really looked into, right? We've just treated them as a source of, like a voltage difference, a source of electrical energy, the thing that causes the current to flow through our circuits. But there are some important details that we'd like to take a look at with batteries that will inform how they act in real life, right? And generally speaking, you can, as long as you're operating within certain constraints, you can treat them like we have been treating them. That's why we start out that way. But there's some detail that is required to figure out how they perform under other circumstances. So if we look at that, okay, first, a little background, right? We got Alessandro Volta inventing the, well, sort of modern battery in 1800. His last name gives us the units for voltage difference, voltage, right? So volta, volt, very nice. And although a lot of engineering has gone into the modern, alkaline battery here, or lithium-ion stuff that we find in so many different electronic devices these days, the basics are similar to what we see here in this lovely museum piece that they have over in Italy, okay? What they've got there is the following, which is a stack of zinc and copper, zinc and copper, zinc and copper, zinc and copper. And what that is effectively a positive terminal and a negative terminal, a positive terminal and a negative terminal, and so on and so forth, all the way down here. So he's essentially put a whole bunch of battery cells in series, and we know what that does, right? That adds the voltages of those battery cells so that you get a larger combined voltage. Now, to elaborate on that a little bit, what he's got here in the museum will not actually produce a voltage difference. Okay, to produce a voltage difference with a battery, you need a chemical reaction that occurs between the electrolyte and the electrodes, which in this case are zinc and copper. So these are the electrodes. And one element, as it says here in the diagram, usually referred to as one battery cell, consists of a negative and a positive electrode, okay, an anode and a cathode, well, actually, cathode, anode, and then this little layer that they have in blue in the diagram here. In the actual battery here that Alessandro Volta invented, that electrolyte was a piece of fabric to prevent electron flow within the battery, okay, because the fabric is relatively insulating, right? It won't allow electrons to go through it. It's not a good conductor like a metal is a good conductor. Soaked in salt water. Salt water was actually the electrolyte material that reacted with these two metals and caused a voltage difference to appear across each one of these cells, okay? The only reason he has a big stack of them is because in the early days of the technology, you needed a whole lot of voltage to push very much current through anything, okay? Light bulbs or, well, that back then, not light bulbs, but whatever electrical powered thing that you might want to do. Well, I guess it was a filament but not like our modern light bulbs, okay? By the way, in terms of how this corresponds to our modern day circuit symbol for batteries, this would be like short, long, short, long, short, long, so on and so forth. So you could see sort of the positive and negative terminals in our terminology, right? So a battery produces its electrical energy from a chemical reaction that occurs between the electrodes and the electrolyte that surrounds them. And the electron flow within the battery is prevented, so it doesn't sort of short circuit, by, in Alessandro Volta's case, a piece of fabric, and in modern cases, essentially a very sophisticated piece of fabric, which is kind of cool. And I want to touch on, other than these basic things about batteries, a couple of bits and pieces about batteries. And in this lecture, I'm just going to talk about batteries in parallel. And we're going to look at something like this. So if we're dealing with 2-volt cells, so each one of these being a cell, one positive, one negative electrode, each being 2 volts, what is the voltage difference between the positive and negative leads here? Okay, so in other words, okay, if we take a voltmeter and we put it here, what would this read? Well, it would read 2 volts, right? They're in parallel, so the voltage difference across each branch has to be the same, and they're both supplying a 2-volt difference, so it's going to be a 2-volt difference. So what that tells us is if we just took one of these batteries and we put it across a resistor or something like that, we'd get a 2-volt difference. And if we put another one in parallel, well, then that would just also put a 2-volt difference across the resistor. So what's the point? Well, okay, so you clearly don't do this if you want to increase the voltage difference across something. But what it does do is the following, okay? For a fixed current output, in other words, you put like a resistor here. It doesn't change its resistance, anything like that, between the positive and negative. The batteries last longer, okay? The idea here is that yes, the total current in the circuit goes through this resistor, but each battery is only pushing 1/2 of the total current, okay, like this. And that means that because battery capacity is measured in amp hours, so capacity of batteries, amp hours, okay? That means that because each one is pushing fewer amps, they last for more hours. And just so you can get a handle on this, if you have a battery with a 10 amp hour capacity, then it can push 1 amp for 10 hours, or it could push 1/2 amp for 20 hours. And so if you are reducing the amount of current that each battery is responsible for pushing around, then they are proportionally going to last more hours, and so the combination of 2 batteries in parallel will last twice as long as just a single battery by itself, okay? Now, the other thing is that every battery has a maximum current output. And so if you have a situation where you have a variable current output, something like an electric motor, which requires a lot of current when it's at low RPMs and developing a lot of torque, well, if you have a bunch of batteries in parallel, then each one of those can supply up to its max current, which means that you can pull, in this case, twice the maximum current of a single battery. So if a single battery can only supply 3 amps maximum, then having 2 in parallel means that you can actually push 6 amps into the attached circuit at a maximum value. Okay, so that's where we'll end up for today, and I will try to get this recording up as soon as I can. See you later.